Castro Alvaredo from University of London, Entanglement Content of Particle Excitations. Please.
Okay, thank you. Yeah, so first of all, thanks a lot for inviting me to be here. It's a great pleasure to be back in Natal. And well, today, as you have said, I come from City, University of London. You see some pictures of our campus in there. And I'm going to be talking about entanglement content of particle excitation. So I'm going to, of course, the title is not very clear, just like this, but during my talk, hopefully I would at least manage to explain what I mean by these words, so entanglement content, and what I mean precisely by particle excitations. So first of all, I'll tell you about where you can read more about this. So the work that we did is actually rather technical at some level. So I won't have time to explain all the details, but if you want to know them, they can be found in 2 recent papers that are on the archive. The first one is a letter-style paper, so it's short, and it's more focused on actually the results, which is what I will present here today. So perhaps this is a little bit more result-based and intuitive rather than technical. And then the technical, longer version of the work, you can find it in this other paper here. So this is work I have done with 3 collaborators. You can see some pictures here. So many of you will know Benjamin Doyon. This is Cecilia De Fazio, who came to City to do a master's project with me and will start a PhD very soon. And this is Ishvan, whom you have seen yesterday giving a talk about, well, a somehow related subject. So Ishvan is a postdoc in my group. Okay, so let me start by explaining in some detail what we actually computed, and then I'll tell you, if I have time, some details about how we did it. So we're talking about entanglement here. So if you know a little bit about my work in the past 10 years, you will know that I have been really working quite intensively on measures of entanglement in massive quantum field theories. So this is what I will be talking about still. So the sort of system I have in mind, although some of the examples I'll give will be also lattices, but the sort of system ultimately in mind is a quantum field theory, a gapped, which is the limit, or I think of it as the scaling limit of a gapped periodic quantum spin chain. So I can represent this schematically in this way. So this is my spin chain with periodic boundary conditions, essentially a circle. We will consider finite length for now. So L, capital L, is the total length of this spin chain, or the number of sides, if you wish. And the sort of entanglement we want to look at is entanglement, the simplest situation, really, almost, which is entanglement between a region of this chain and the rest. So this is subsystem A with respect to B, or vice versa. And this subsystem A consists of little l sides, so it's of length little l. Okay? And as I said, we will be focusing on the gapped case. So we are not at criticality. There is a correlation length that is finite. So what kind of quantities I'm going to be talking about are very well-known ones that have featured already, for example, yesterday, Maurizio's talk. So a common measure of entanglement are the Renyi entropies. You have already seen. I flashed them in here. And for this particular problem, in general, Renyi entropies will be functions of these 2 length scales that are involved, of course, in the problem. And they depend on a parameter n. Maurizio was calling it alpha yesterday, but it's the same sort of parameter. And this rho A here is the usual reduced density matrix where you trace out the degrees of freedom of subsystem B. So essentially you ask, what entanglement does A have with respect to B if I forget about B, essentially, if I forget about the environment. Now, what is new about our results, or what we investigated in these 2 papers, was actually the situation where we have zero temperature. Okay, so it's simple still. We have the system in a pure state, but that state is not the ground state, it's an excited state of a certain type in QFT. So in the past, we have done a lot of work about describing aspects of the entanglement in the ground state. So here we wanted to go beyond that and look at certain types, at least, of excited states of interest. So in my talk, this phi here and this phi in there will always be a certain kind of excited state. So if you know the Renyi entropies, then there are other entropies that you can easily access. I think many of you will be familiar with that. You can easily compute the von Neumann entropy, which is the limit when n goes to 1 of your Renyi entropies. And just to make things a little bit shorter, in my talk, I'm going to indicate this entropy by S1. So I mean the limit when n goes to 1 in here. And there is also another type of entanglement measure that some people have studied, especially in the context of quantum info, which is something they call the single copy entropy, which is just the limit when n goes to infinity of this same quantity. Okay, so I denote that by S infinity here for the same state. So I'll be showing you some results for these three quantities here for some kinds of states. So what kind of excited states am I thinking about? Let me tell you a little bit about that. So, I mean, I'll mention the literature also a little later, what other people have done. But the sort of excited states we have investigated are what you can call zero particle density states. So these are states that consist of a finite number of particle excitations. And if you are familiar with 1 + 1 dimensional quantum field theory, then you will be familiar with this kind of representation of such states. You also saw it actually in Istvan's talk yesterday, so he talked about this kind of theory. So if you're in 1 dimension, you can represent particles or excitations by their momenta or alternatively their rapidities. So these thetas are the rapidities. And so we are thinking of a state where we have k particles with k rapidities, which will be equal or distinct. We'll discuss that. And with k different set quantum numbers, you may have a complicated theory where many different types of particles can arise. But what is important is that this k is a finite number. So we have a finite number of excitations. And in terms of actually what Mauricio explained yesterday in his introduction, these kind of states, you might think they're not very interesting because I think from the energy point of view, they are not very far above the ground state. So you would expect that their main entanglement properties are very similar to the ground state. And they actually are, but what is interesting is that if you look at the difference between their entanglement and the entanglement in the ground state, you find that that difference has some universal interesting features, and it's non-trivial, actually. It's a non-trivial function. So this is what we have been looking at. I'll tell you more a little later. Now, it turns out that if you try to do a computation of these entanglement entropies in a quantum field theory that is not critical, it's actually not that easy to do the calculation. And so the simplest thing you can start with, of course, are free theories. So in the second paper I mentioned, the long one, we actually did an explicit computation for free fermions and free bosons. We think that a lot of our conclusions will really extend unchanged to interacting theories, but that's a computation we still have to do. We actually have quite a bit of evidence by now, by different means, that our results apply to a wider set of theories, so interacting theories, but also even in other dimensions and in other geometries, so even in higher dimensions. And I'll tell you a little bit about that later. An interesting thing that we found is that, so if you look at that kind of state for theory of a free fermion or a free boson, if you have free fermions, then you need the rapidities to be all distinct. So you cannot have fermions all in the same state, as we have heard. So in the case of free fermions, the only kind of state we can consider are the states of distinct rapidities. But if you look at free bosons, it is possible to consider also states where some of the rapidities coincide, are non-distinct. And it turns out that there is really a marked difference in the features of entanglement, whether you are in a situation of undistinguishable particles or distinguishable particles. So in the free boson case, there is this additional feature that's interesting. It is, of course, fair to mention other studies that have inspired us to do this work and that also helped us to understand our results better. The study that I think was most inspirational, at least for me, when we started looking at this, is the work of Germán Sierra and his collaborators that goes back a few years already, where they looked at a similar problem, but for critical systems. Okay. In quantum spin chains, actually, I think the most extensive and detailed study of a critical spin chain is in this work, actually, by Vincenzo, Maurizio, and Pasquale from a few years ago as well, where they really looked at many different kinds of excited states in these models. Although I think, from my understanding, that they were often looking at non-zero particle density states. So it was really quite a different situation, and it was critical as well. And then there is also a work that we became aware of when we talked to Vincenzo as we were doing this, by Vincenzo and other people, where they looked at actually excited states in the gapped XXZ chain. And in that work, actually, they have some results which connect directly to what we did. And that also was quite interesting for us. So sorry if I didn't mention some other relevant works, but these ones were quite inspirational, important for what we did. So let me tell you a little bit more precisely exactly what we computed, and then I'll show you what results we got. Because the results, actually, they are hard to get, but when you get them, they're actually very simple, and they're easy to explain without giving you technical details. So what we looked at was actually not directly these entropies I presented to you, but rather the difference between entropies in the ground state and in one such excited state. And this is exactly the same kind of quantity Germán Sierra and others studied in their work. So in their work, actually, they call this the excess entanglement. So they interpret this as the additional entanglement that is added to that of the ground state when you have a certain type of excited state. So this is exactly the same thing we did. Now, if you try to compute that in a quantum field theory, actually, even in CFT, it turns out that it's rather complicated to compute exactly. And in massive QFT is even more complicated, actually, to get the exact form of those functions. However, what we found is that there are certain limits, well, there is a certain limit where we can have exact results. And this is really what we computed precisely. And the limit that we looked at is a scaling limit in which both the size of the region A and the size of the system go to infinity simultaneously, but the ratio is kept fixed. Okay, and that's rather important. So the ratio between these two length scales is, I'm going to call it little r from now on, is a dimensionless quantity between 0 and 1, obviously. Okay? So whenever you see little r, this r in here. Okay? So what do we find? So we computed something like this. So Sm phi, these were the Renyi entropies of this excited state phi. As I told you, they are functions of little l and capital L, but now little l can be written like this, r times capital L. And then if we put a delta in front, that means the increment. So the difference between the function in this state phi and the function on the ground state are indicated by 0. And what we find is that when you take the limit L to infinity, this difference is a function that depends only on this little parameter r and on nothing else. It actually doesn't even depend on the energies of the excitations and all these rapidities I showed you earlier, which is quite an interesting and, universal result, surprising result it was for us. If you look at finite volume, so if you look at higher volume corrections to this result, so this is the result for infinite volume. If you want to look at finite volume corrections, then those will depend on the energies of the particles and on more detailed features of the model. But if you just want to look at this leading contribution, this actually just depends on R and seems to be highly universal. That is kind of the most interesting thing about the result. Okay, any questions so far about what we are computing? Because now I'm going to start showing you some results. Okay, so the same holds for the other entropies I mentioned before. Okay, so let me show you some results. I'm going to start by showing you the result for the simplest excited state that you could possibly imagine. This is the first one we started doing computations for, obviously. And this is the situation when you have a single particle excitation. So you have an excited state with one particle of a certain rapidity, theta, a fermion, a boson, or something else. So what is the change in the Renyi entropies for this one particle excited state? What is the increment? Well, these are the formulae. Okay, so they are extremely simple. So if you look at the increment in the Renyi entropies, okay, there's the arrow there. If you look at the increment of the Renyi entropies, you see that the change in the Renyi entropy is just the logarithm of a very simple polynomial on this variable r that was between 0 and 1, the ratio of the length scales. If you take the limit n to 1 of this, you get the contribution to the von Neumann entropy. And you see that it takes a very familiar form, this r log r minus 1 minus r log 1 minus r. And then if you look at this so-called single copy entropy, which is the limit when n goes to infinity, what you get is a function that has actually cusp exactly for r equals a half. Okay? Actually, it's very easy to plot these functions, obviously. So here you have a picture just to give you an idea. So if you look at this picture, all of these curves in different colors, these are any entropies for different values of n. The outermost curve, this is the von Neumann entropy, which is that function there. And the innermost curve that has a cusp, just here in the middle, that's this single copy entropy, okay? You see that all of these functions have a maximum in the same place, at r equals a half, exactly, and the maximum is log 2, which is actually quite a satisfying, nice result. Essentially, it tells you that the maximum contribution to entanglement that a single excitation can make is exactly log 2, which is something that you would intuitively expect. And actually, there are papers before ours, for example, by Vincenzo, and even a little earlier by Pizorn, where he provides actually some quite general arguments as to why the maximal addition to entanglement from an excited state has to be log 2. Okay, so that agrees with that. I would like to emphasize, because I think that has caused a bit of confusion in previous talks I gave about the same thing, that if you look at this von Neumann entropy here, remember this R here has nothing to do with thermal, with the Yang-Yang entropy. Although this formula looks like the Yang-Yang entropy, this R is not accounting of configurations. The temperature is 0 in this problem. There is no temperature. This R is just the ratio of the length scales in the problem, okay? Nothing else. Now, if you keep looking at these formulas and think a little bit more, what you realize is that actually they have a what you realize is that you can actually very easily construct a very simple quantum state that would have exactly these entanglement entropies here. A much simpler state than the ones on how we started with. And the sort of state you can imagine is a qubit state. I call this phi qubit, which is a state consisting of just 2 qubits. I give them values 0 and 1, with coefficients which are exactly root of r and root of 1 minus r. So if you compute the entanglement of the first qubit with respect to the second one, for this particular simple state here, you will get exactly the same formula I just wrote in there. So what does this mean? Well, it means that somehow this contribution to entanglement of excitations has a very simple interpretation in terms of qubits. And the interpretation is that somehow it looks as if that entanglement is telling you about, well, the probability of finding that excitation either in region A or in the rest of the system. So if you look at that state here, what it's telling you is that essentially the state 1 is the situation where particle is in region A with probability root r, and the state 0 is the situation where particle is in region B, the rest of the system, with probability 1 minus r. So it's as if the entanglement, at least at leading order in infinite volume, only cares or only looks at the fact of whether the particles and how can be found in region A or on region B. Okay? So it tells you something about particle content, that hence my title. Okay? Any questions about this so far? Okay. So this is the simplest case, and then you can, of course, look at other states that are more complicated, and we did that. So we describe every possible kind of state of this type. So the next thing you can look at is at a state where you have now k particles instead of just 1, and you can think of a state where all of these particles have distinct rapidities, distinct momenta, okay? So they're all distinguishable from each other. And if you do a calculation for such a state, what you find is that the results are exactly the same multiplied by k, okay? So essentially, each of these particle excitations gives a contribution which is exactly the same as of a single particle state, okay? So if you want to do a picture of these functions, this is an example for a state of 3 particles with 3 different rapidities. You see that all the curves are the same multiplied by 3. So now the maximum is 3 times log 2, and everything is really the same. And you can also give a qubit interpretation to such a result. You can also think of these entanglement entropies here as simply the entanglement entropies of a qubit state consisting of 6 qubits, where each of these qubits represents whether the particle 1 is in region A or B, whether particle 2 is in region A or B, etc. Each of them with probability root r and root 1 minus r. So for example, this one here is the contribution from having all 3 particles in region A, each of them with probability root r. Okay? So so when you look at this, somehow it looks, yeah, somehow it makes sense intuitively. It's very simple. I'd really like to emphasize that it really, I mean, we didn't expect these results at all, so when we did our computation, so it was really a big surprise for us to do this long quantum field theory calculation based on form factors and then eventually come to results that are so simple looking and have such a nice interpretation. Okay, so let me show you the situation when you have now particles with equal momenta. So I told you earlier that if you have a free fermion, you cannot have this kind of states. But if you look at a free boson or other theories with bosonic statistics, you can potentially have a state with many particles which are identical and distinguishable. And this is the sort of state I want to look at. So k particles which are all identical to each other. And in this case, you find a slightly different result, but still with a nice interpretation as before. So there is now a function that is going to play a role in here. There's this function there. And this function here essentially is a function that measures the probability of finding q of these k particles in region A and k minus q of these k particles in region B. And because all these particles are undistinguishable from each other, that probability now carries a binomial coefficient, just to count that fact. Okay? So in terms of this function here, the Renyi, von Neumann, and single copy increment of the entropies, they now take forms such as this. So you always have sums over powers of this function there. Okay? So this function becomes the building block. What you see in particular for these single copy entropies is that now they develop several cusps. So for a single excitation, we had a single cusp in the middle. Now when we have many identical excitations, we're going to have as many cusps in this function. And here I show you a few pictures just to get an idea of what these functions look like. So again, the outermost is von Neumann, the innermost is single copy, and in between we have different Renyi entropies. And you see that if you have 3 identical particles, this single copy entropy has now 3 cusps. Okay, and there is also, of course, a qubit interpretation of this result, a state that you could write that will give you the same entropies. And in this case, it's a state that looks like this, with 4 qubits, which essentially tell you whether all 3 particles are in region A, or 2 are in A and 1 is in B, etc., with their respective probabilities. And these probabilities are now altered by some coefficient, which is this binomial coefficient there, okay? Telling you that all of these particles cannot be differentiated, okay? So finally, you may want to look at completely general states where some rapidities are equal and some are different. So we also looked at that. And if you do an analytic calculation, again, for free theories, it's very easy to convince yourself that for such states where you have k1 particles of rapidity theta 1, k2 particles of rapidity theta 2, etc., for such a state, the result is just a combination of the formulae I showed you earlier. Okay, so essentially, if you have, as I said, k1 particles of rapidity theta 1 and so on, then their rapidity will be the sum of the Renyi entropy for this set of identical particles plus the Renyi entropy for the next set of identical particles and so on. So the results are additive. And here are just a couple of examples just to show you what these functions look like. So this example is, for instance, a state where we have 9 particles. 4 of them have the same rapidity. 3 of them have the same, another rapidity. 1 of them has another rapidity, and another one has yet another rapidity. So we have 4 different rapidities, and these functions look like this. You actually see that both here and in my previous case of identical rapidities, you find that these functions, they all have their maximum still in the middle, as you would expect, but the maximum is not the same for all of them. And in fact, when you have repeated rapidities, what you find is that the maximum is always lower than if the rapidities were distinct. Okay, so it's always smaller than k times log 2, if you wish. Here's another example and another one with different choices of how many particles have same rapidity. So 2 and 3, 1, 4, and 6, etc. So you can amuse yourself doing all sorts of pictures, and you see that all these cusps somehow are still there, but they get kind of smoothed when you add all these functions. Okay, so these are the analytical results. Okay, now once we got all of this, and we had this nice qubit interpretation for all of these results, we started thinking a little bit And then we thought, well, if this qubit interpretation really is to be taken seriously, then actually, somehow the fact that the system is one-dimensional shouldn't be that important. Because somehow, it looks as if the entanglement is just telling us whether the excitation is in a certain region or is not. And so why not looking at things in higher dimensions as well? So we decided to check that, and we also decided to check these results in some way. So the way that we checked this first was by doing a numerical simulation. And the numerical simulation we did was a simulation of a harmonic chain. So a harmonic chain is a discrete system whose continuous limit is supposed to be a massive free boson. So we would expect that in a certain regime of this harmonic chain, we will recover the free boson results. So this formula I'm showing you. The method that we used to do our simulation is actually a numerical recipe Benjamin developed himself. He called this the wave functional method. What's important about the method is that it's an exact diagonalization method. Okay, so in other words, the only error that is in this method is due to the fact that the volume is always finite. We can really go to exactly infinite volume, but we were able to go to quite high volumes. Okay, for this model, the dispersion relation looks like this for the harmonic chain, where delta x is the lattice spacing, and p will be the momentum of whatever excitation is there. And so what you see is that essentially when the function inside the sign is smaller than 1, then this dispersion relation becomes the QFT dispersion relation, m squared plus p squared. And so you would expect that for choices of p and delta x that satisfy this condition, you might find agreement with the formula I showed you, which we got from a QFT calculation. So let me show you some examples of that agreement. So the first picture I'm showing you here corresponds to this particular choice of parameters. So this m is the mass scale or correlation length, if you wish. And in this particular example, there are 3 particles. So we are looking at the Renyi 2 entropy, so n equals 2, of a state of 3 particles. And there are 3 curves in here, because for 3 particles, we may have 3 equal rapidities, 3 distinct rapidities, or 2 equal and 1 distinct. These are the 3 results in there. Now, all of the continuous curves in here are my functions that I showed you earlier, and the dots on top are the numerical results from this method. So they agree very, very well, really to, huge precision, really machine precision. So it's absolutely in agreement, it works, so that's nice. Now, what's interesting is that you can look at a different regime of parameters, and then what you find is that even when you are not in this QFT regime, you still find agreement with our formulae. So that kind of suggests that this formulae, although we computed them in a certain situation in QFT, they seem to hold much more widely than that. So for instance, here this is a plot of the Renyi entropies for various n's for one excitation, a state of one excitation, one particle. And again, you see perfect agreement, so all the dots fall exactly on top of the curves. You can almost not see them, but these are numerical values. And this plot here is for actually a choice of parameters that is quite different. So here the momentum is quite large. Delta x is the same as before. L is actually not very large compared to the correlation length. So in fact, this condition is really not satisfied in this case. But what is satisfied instead, actually, is that in this particular regime, what you have is that 2 pi divided by the momentum of this excitation is of the order of the lattice spacing. Okay, so this is the regime of this curve. So in other words, in this regime, our particle is really seeing the lattice structure. You can say that this is a non-universal regime, it's not QFT, but the agreement is still perfect. Now, I don't have time to show you more plots and more things we explored, but just to conclude, what we find, in fact, by looking at different cases, is that in general, if you want to have this formulae to hold, we need a regime where this condition is satisfied. So essentially, it's as if there were 2 correlation lengths in the problem. So there is the correlation length associated to the theory, whatever it is, the inverse of the mass scale. But then there is another scale here, which is what you would call the de Broglie wavelength of these particles. So these particles themselves, they have an associated wavelength. You could think of it that way. And if either of these quantities is smaller than the size of the interval that we are looking at, then in some sense we can still think of that excitation as a localized excitation. And as long as we can do that, whether this is QFT regime or another regime, these formulas seem to hold very well. Okay, that's the conclusion. Now, I told you a bit earlier that from all I told you, there seems to be no reason why this shouldn't hold in higher dimensions too. And this is a hypothesis we made at some point, and we decided to test that as well. So I'm going to show you a few other numerical results for 2 dimensions, for a harmonic lattice. Okay, so this is actually, I've already told you. So our hypothesis is that, or was that, somehow we get this formulae, which just depend on this ratio of length scales in infinite volume. So if we go to higher dimensions, everything should be the same. That's okay, what we suggest. Everything should be the same, but this parameter R will now be replaced by the ratio of the d-dimensional volumes, whatever the dimension d is. Okay, so the volume of region A divided by total volume. This is still a dimensionless quantity between 0 and 1, and we propose that our formulae will hold in the same way, but now depending on this R, defined in this way. Why do we think that will work? Well, there are some situations where there is quite some clarity that it will work. One such situation is a situation where you can do dimensional reduction. So here I cite this paper, not because, I don't think dimensional reduction was introduced there for the first time, but I know that it was used here in the context of the study of the high-dimensional free boson. And essentially what you can argue is the following, that suppose that you have this example. So this is my system now, it's 2-dimensional. Okay, so that's region A, region B. Suppose that I start with a region A that has, well, kind of a horizontal dimension that is rather small. The vertical dimension is the full length of the system, the full width of the system. And now I grow the size of A in this way. I just grow it horizontally until I get to half the system. Now, if I grow my region in this way and I look at the entanglement, in effect, although the system is 2-dimensional, in effect what I'm doing is still 1-dimensional, because the only thing that I'm changing is the horizontal dimension of this subsystem. So this is an example of a problem that would be amenable to something called dimensional reduction. So the suggestion is that everything will, the results will be exactly the same as in the 1-dimensional case, because only the horizontal part really matters. Okay, and this can be phrased, at least for free theories, this can be phrased more precisely in terms of free boson fields, and you can show that there is actually a 1-dimensional boson that you can define along that direction, etc. Okay, so that's a little bit cheating. You would expect things to work in there, but what we have found in the harmonic lattice is that even when you grow subsystem A in a way which is not amenable to dimensional reduction, so you grow it in both directions, you still have very good agreement with our formulae. So let me show you that in one example. So here you have 2 curves. This is the Renyi 2 entropy, again, n equals 2, for an excited state of 2 particles, I think. Phi, yes. Yes, this is 2 particles, I think. I didn't write it, but I think it's 2. So we compute the second Renyi entropy. We computed it in a square, so a toric lattice of a certain length L. We were able to go up to 50, which is not that big, but it was enough. Lattice spacing is 1 in our numerics. And what you see here is 2 curves, because this is a 2-particle excited state, and so you can have the situation where the 2 particles have distinct momenta, so they have more entropy, or they have equal momenta, in which case the entanglement contribution is a bit smaller. So you have, again, 2 analytical curves in there. And on top of those curves, you have perfect agreement with some numerical data. In fact, on top of each curve, there is actually 2 sets of numerical data, although you can hardly see them, but there is a square, and inside each square there is a cross as well. So the squares, they correspond to QFT regime, essentially, in the sense I defined it earlier. And the crosses, they correspond to non-universal regime, also in the sense I defined it earlier, where you are not in QFT, but the de Broglie wavelength is sufficiently small. Okay? So as you can see, in all cases, agreement is very good. The way we grow subsystem A in this case is it's always a square, and it gets sort of bigger and bigger. So you can think of it like this gradual process here. And what's kind of interesting is that now when you get to this configuration, suppose that if this was accurate, it's more or less accurate. Suppose this is the configuration where R equals half, so the ratio of the areas of subsystem A and B is exactly half. You see that contrary to the one-dimensional case, geometrically A and B in this case, they don't look alike at all. So it's not a symmetric situation. Still, our curves are completely symmetric around this point, R equals a half. Okay, so it's kind of non-trivial to see. And well, it's a nice observation to see that this holds in 2D, and I mean, it seems that will probably hold in higher dimensions than 2 as well, but we didn't explore that. Now, another thing that one can explore numerically as well is the finite volume corrections. So when you do numerics, of course, you can never have exactly infinite volume. And so there will be corrections to these results, and then you can try and investigate those. And we did that a little bit. We want to do a bit more in the future. So let me show you a couple of examples of what you can do with these corrections. So I have here 2 pictures, which are actually very similar. And I'm computing really, or we are computing the same quantity in both. It's just that one is for harmonic chain in 1D, and one is for harmonic lattice in 2D. Okay? And in each of them, what I have done is I have taken the top of these curves, so the maximal point of these curves, for the Renyi 2 entropy of a single particle excitation. So for single particle excitation, the maximum is always at log 2. And so what I do is I take the entropy at that point, and I subtract log 2, or rather the other way around, log 2 minus the entropy, okay? Because log 2 is the maximum. Now if I subtract log 2 minus the entropy, and I take the log of that, and I plot it in a log scale with respect to the volume, well, what I find is this result here. So essentially the difference is rather small, but still there are corrections which depend on the volume. And for volumes which are around 1 and a little higher, you see that those corrections in a log-log scale, they tend to coalesce along a line, okay? So and this is the same for the lattice as well, it's just that the slope of that line is slightly different in both cases. So what this tells you is something that you actually expect from quantum field theory, namely that there are finite volume corrections and that they are of algebraic type. So they're going to be of this form here. So in general, you'll get R results plus some function of the rapidities, probably, divided by L raised to some power. If you actually do a fitting of these lines in there, you see that for the harmonic chain, the power seems to be about 2. Okay? Of course, this is not precise, but I think if we include more points and so on, it seems to tend towards the value 2. So it seems the first correction goes like 1 over L squared. If you look at the lattice, the coefficient is a little bit smaller, and actually, it seems that it doesn't become an integer. I mean, we did a bit of exploration, and it seems to be this strange number. So we don't really have an interpretation for this, because we only have numerics for higher dimensions. But it would be interesting to understand in the future, I mean, what these numbers come from and whether you can compute them or not. In 1 dimensions, you can probably compute them, but even for free theory, it's actually extremely hard to access these corrections. Okay, so any questions so far? I have 5 minutes, okay, only. So I haven't told you anything about the techniques that we use to compute this, and I have 5 minutes left, so I'm not going to be able to tell you a lot, but let me just tell you maybe a couple of ideas, the main ideas, and then if you're interested, you can ask me or look at the papers. So essentially, there are 2 techniques that we used. One of them is something that if you ever heard a talk by me in the last 10 years, you won't be surprised. We use this because this is what we have been doing for a long time, to use something called the branch point twist field approach to entanglement measures. Now, if you never heard of this, you're not going to learn it today, for sure. But the idea of this technique is that this difference of Renyi entropies and their corresponding limits in quantum field theory, both at criticality and beyond criticality, can actually be expressed in terms of a ratio of 2-point functions, of some local operators. These local operators, we call them branch point twist fields, okay, for some reason. And these fields, T and T tilde, in here, they are related to each other. They are actually Hermitian conjugate to each other. Now, okay, so we have 2-point functions. This is the 2-point function in the excited state. This is the 2-point function in the vacuum. You do the ratio of these 2 things, and that gives you these functions. And take the limit volume to infinity, that gives you our results. So when I write L in here, on the sides, I mean that these are finite volume correlation functions, similar to those Ishwan was talking about yesterday, actually. So why do we want to have finite volume? So in the end, we want to take volume to infinity. So you might think, okay, why don't you take volume to infinity from the start? Because actually, for example, when you study entanglement of the vacuum, normally we start with this correlator and we compute it directly at infinite volume, and there's no problem with that. The issue is that when you have a state here that is not the vacuum, that is non-trivial, then actually it's difficult to compute this correlation function directly in infinite volume. And the main reason is that essentially this correlation function has singularities whenever there are some coinciding rapidities emerging, very similar to what Ishwan was explaining yesterday, in fact. So essentially there are singularities in this function in infinite volume, which is hard to deal with. And one way to deal with them is to compute it in finite volume and use the volume as a regulator for those singularities. So you do your calculations at finite volume by some technique, and then at the very end, you take volume to infinity, and then you are sure that you're getting the correct finite part of your result. Okay, so this is a technical aspect, but that makes the whole problem actually a lot harder, because finite volume correlators, they're actually not that easy to compute. And for these branch point twist fields actually haven't been computed before, so the whole challenge was in there. So how try to develop this branch point twist field program for excited states and in finite volume. Okay, so even for free theories, that was rather non-trivial. So I think that's probably all I have time for. Really, I had some more details in here, but it's really not that important that you get those. It's okay. Maybe I'll show you, here's a couple of statements. So if you do this calculation, okay, of these finite volume correlators, what you actually find is that at finite volume, this correlator has a natural 1 over L expansion, okay? And therefore, the fact that we see 1 over L corrections to our results is not surprising. This is what you expect from QFT, at least in 1 dimensions. And in 1D, in fact, you are a priori able to find precisely the form of these corrections. A priori, you could compute those, and that's something we still may do in the future. Now, the interesting thing that you observe is that when you look at the limit of L going to infinity, of course, all those corrections go to 0. But crucially, we were able to prove that there's always a term that is independent of the volume. It goes like L to the 0. So the leading term goes like L to the 0. And that's the reason why, when you take the limit, there is still something non-trivial left. Okay? Otherwise, you get just 0. Okay? Now, here's a formula that is completely meaningless to you because I haven't explained you how you get in there. It just gives you perhaps an idea of the look of things. So this is a formula for the ratio of the two-point function of a single excitation over the two-point function in the vacuum for these fields. And generically, what you find are expressions like this. So you have big sums over a certain partition, which is related to some set of rapidities of intermediate states you put between those fields. So these are some coefficients that have to do with the way you represent that state in a certain suitable basis. And then there are some functions that appear. These functions here, G. And these functions I just flash, just for your information, I just flash the form that they have. So you get some functions that appear all of the time in these computations. And they look like this. So there are sums over integers of some function which actually turn out to be a simple polynomial on this little r variable. And because they are simple like this, that's the reason why eventually after you do all these products and sums, you end up with things like that, simple things, okay? But it wasn't really easy to spot a priori. So when we did this calculation, we started doing a particle, n equals 2, n equals 3, n equals 4, and then we said, okay, there seems to be a pattern. Let's see what it is. Eventually, we realized what was happening. So what is interesting about these functions is that they arise naturally when you look at the behavior of form factors of these fields near kinematic poles, okay? And that suggests a certain level of universality for this formulae. Okay, so actually let me give you the conclusion, okay? So I'm finishing. So I presented a set of QFT techniques to you that allows us to explore entanglement for a finite number of excitations, and actually to show that there's still some non-trivial information in there. We are able to get analytical results, at least for free theories so far, But something that is interesting is that some of the formulae I showed you, at least, they actually appeared in the paper of Vincenzo for the XXZ gap chain, and in there they are described as the semi-classical approximation. And what they observe generally in the chain is that these curves are approached essentially when the chain is made bigger. Okay? Our work somehow says that it's not even a semi-classical approximation. It seems to be more general than that. Actually, they emerge from a full-fledged QFT computation. Our derivation incorporates the effect of undistinguishability, so there is an effect of repeating momenta or not. And the formula seem to hold in a large variety of situations, which is what makes this result really most interesting. So not just QFT in one dimensions, but also in other regimes, in 1D, and even in higher D. Okay? So they seem to capture something really very fundamental. We are pretty sure that these results are going to hold for interacting integrable models. There are several reasons why we think that. One reason is that the form of the results that we get at the level of computations is really fully determined by the kinematic pole structure of form factors. Okay, that is technical, but those of you that know form factors will know what I mean. And that pole structure is actually very universal. It doesn't really depend very much on whether the theory is interacting or not. And so we expect that this will go through, but it's harder to compute, for sure. This is also supported by the qubit picture. So in this qubit picture, remember, somehow, the only thing that seems to matter is whether the particle is localized somewhere or not. And as long as you don't have particle production, which is a feature of integrability, we don't see why kind of this picture will be altered. There are also some calculations one can do. Some of them are also given in the paper of Vincenzo already. So it's actually very easy to convince yourself if you take states such as these here. So these are two typical states in a spin chain, where this J here, for example, represents a state where all spins are down except the one at position J that is up, let's say. Let's imagine this is the XXC chain, and these P's are the momenta. And here these are two particle states. So you have a 2 magnum state and a 1 magnum state, if you wish. So what is interesting is that if you do by hand a calculation of the entanglement entropy of these states, for example, Renyi 2, which is the easiest one, for the one particle, actually, you can do any Renyi entropy, and immediately you get the R to the n plus 1 minus R to the n. It's really trivial to get. For two particles, you also get that. And even if you have a non-trivial interaction matrix in here, you still get the same result. So this is a strong suggestion that interactions are actually not that important. So actually, for any excited states of spin-preserving quantum chains, even non-integrable ones, potentially, we expect these results to hold. It would be nice to see this. If there's particle production, then perhaps there are changes, because you could imagine if there are more than one excitation, then there could be interaction that destroys this nice qubit picture. And well, something I mentioned already is that next to leading order corrections, technically they're also interesting. So with this, I'll conclude. I'd like to thank EPSRC for funding us, me and Ishvan, in fact, in particular, and Benjamin, actually. And this is the end. Okay, thank you.
Okay, time for one or two quick questions.
Yeah, I think I can hear.
Yes, so especially for the free fermion case, if you put in a lot of particles, you should be able to get to some thermal limit of your answer. Can you see that?
Well, I don't know. So, I mean, thermal seems to be strange because there's no temperature, T0 in this problem. We start with a pure state. But it is true that somehow there should be a sort of crossover limit, in a way, of our formula, going from a finite number of excitations to an infinite one. So going from zero density to finite density. We haven't explored that. I mean, from the computational point of view, that's probably a rather non-trivial limit, I think. But it would be an interesting thing to see what happens when you take a limit of infinitely many particles in the state. We haven't really looked at that.
Okay, thank you.
Any other? Oh, there we go.
But in the presence of interaction, you will still expect that the things are factorized like that? I mean, that you're... Is it because the volume is large compared to the number?
Yes. So, I mean, I think, well, I mean, we haven't done the calculation. We're trying to do it. But somehow from what we have seen, technically, we think that in this particular limit, which is just the leading contribution, the order 0 in the volume contribution, we think it will still be of that simple form. And the reason is what I said, that somehow these kind of functions that appear, these G functions I introduced at the end, they essentially just emerge from looking at the, essentially the leading form factor contribution around, the leading two-particle form factor contribution around its pole. Okay? Now the residue of that form factor is determined by the equations, as you know, and it's the same whether you have interaction or not, pretty much. So I suspect you will get a similar factorization. And from the numerics and the chain and everything else, there's a strong suggestion that that should work. But at the technical level, it's a bit harder to access that for different reasons. So we're still working on it. Especially Ishbang, I think, is working very hard on it. Okay.
Okay, so there are no more questions. Let's thank the speaker again.
Thank you.
That concludes the morning session. We're all ready for lunch.